Hello everyone and welcome to a continuing discussion on the possibility of interstellar travel, partly brought on by a video by Kurgasagd. And we are going to broach in this video the subject of incoming debris. Now, incoming debris is a big problem because if we've got a vessel that's traveling at a certain fraction of the speed of light, the stuff that's going to be coming at us is going to be coming at us at a very, very, very high speed and therefore have a lot of kinetic energy. If it's sufficiently large debris that's coming at us, then we are going to be able to use our RCS thrusters to get out of the way. It doesn't require us to, change our velocity very much. We just have to sort of sidestep by a few meters and avoid the debris. Well, it depends on how big our rotating habitat ring happens to be. It's possibly 100 meters in diameter. It depends on how we're generating our artificial gravity, because on a trip this long, we're going to need to generate artificial gravity. So we've got a big artificial gravity ring to protect, and we've got incoming debris, and some of it is stuff that we're not going to be able to detect. Now, in Kurgasag's video, there was a whole lot of shielding in front. And the thing about spaceship design is, you really don't want to have something providing only one function. And so that's the main topic of this video. For instance, in my Aska spaceplane, I have it using water for the radiators. So it's a titanium water radiator. But that also has the benefit of serving as the radiation shielding from the spaceplane's reactors. So it's got two 100 kilowatt reactors, relatively small, and it's got the water tanks in the way between the reactor and the crew. So it's providing the neutron radiation shielding like that, so that the water is doubling up. It is not only the water for the radiation shielding, it is the water for the radiators to dissipate the heat. And so that works. And you want to do that as much as possible if you're going to make your ship efficient. So what can we do in our situation where we need some shielding in front to block little particles so that they don't have little plasma explosions at us? Well, we have another component that we need on this that I haven't included yet, and you might have noticed that. In other words, radiators. But it wouldn't be good for a regular radiator to be out in front, because then you got a hole in your radiator, you're losing radiator fluid, and that's no good. But what if your radiators are already something that sort of leaks, if you will? Now, this is perhaps a bad example because I made these liquid droplet radiators with gaps in this bit, but you don't need the gaps here. They don't need to be made with these little holes, so you can't make them just straight out. But it's just a figment of modeling that we have these gaps here. But what liquid droplet radiators are is that little droplets are emitted from the frame and then caught at the other end and allowed to cool along the way. So these are little metal droplets, and they are efficient in being radiators because they can radiate in all directions, because they're just little spheres that are able to emit instead of panels. And I've got these lined up a little bit wrong, but forgive me. But the idea is that now you have a regenerating shield, because these are droplets that if something impacts them, yeah, they're going to have, maybe a plasma explosion or something like that if they intercept it, but there's other particles that are going to be covering the gap pretty soon. So it doesn't really matter. You've got a regenerating shield, and it's doubling as the thing that is dissipating the heat. I don't think we have enough here for that purpose right now. Not quite enough. We would need more radiator capacity for the 547 megawatt reactor I've got in the back, which is fusion. But there are downsides to this. If you are going to use this as your shielding, you're going to have the droplets pretty close together, so they aren't as efficient as they normally would be if they're spaced out a little bit more. If they're oriented like this, if the radiators are oriented like this, some of that heat's going to come back at the habitat. But we are actually going to deal with that partly. Another thing is you do still have to have bumper shields over the frame. which is doing the liquid droplet emissions. So you're going to have to reinforce those so that they can take impacts with layered shields. But that's a heck of a lot less than having to shield the entire area for the habitat. And the habitat's going to be much larger than this apparent area, but that will be just about right for the shielding that we are going to need for our big reactor. And we don't need just one layer. We just need to make sure that they are spaced out a fair amount. So, and we're going to do more here. This is not the end of the story. So it'll be much more extreme than this, and everything will be built in orbit, right? We are not going to try to launch all this. That's why we need to have resource development in the rest of the solar system before we do this. So we have multiple layers, and along the way the ambient temperature will cool them, but they would have to be spaced out pretty far. But as long as you're building it in orbit, it's not that bad a deal. And the extra mass of this arrangement is actually very, very low. And that's just to cover, I've got an estimate. Even if you had liquid droplets that were super close together, so they would block 99.99% of incoming particles. And so they wouldn't be radiating as efficiently as you would like them because now they're really close together. But they can block practically all of the stuff that's coming at you. Even with that, you would be able to cover a 1,000 meter square area with just 1 ton of liquid droplets. So the frame mass is going to be most of it. The liquid droplet mass isn't going to be a big deal. And it's a huge saving over trying to do anything with regular radiators that are fixed as opposed to liquid droplet radiators. So we've got this arrangement. But that is not the end of the story, because maybe we don't want them that close together, right? So in the middle here, we can put something else that has a dual purpose. And that is the fuel that we need on the way back. Assuming that we want our crew to actually come back from another star system, it might not be the same generation of crew coming back, but if we want to, what we can do is put the fuel for the deceleration on the way back to Earth, into Earth, up front. And in separate sort of tanks up front. And then what you have is basically a hydrogen shield like that. Hydrogen, people think very badly of hydrogen under normal circumstances, but hydrogen does have the nice benefit of not being very dense. So if it's not very dense, it's got to take up a lot of volume anyway, and then you can just fill up a tank like this with the hydrogen and have it be the buffer. You need it anyway. You need it anyway to slow down at the other end. This is not enough delta V to do anything, by the way. That's because we're not using the kind of reactor. I haven't developed the kind of reactor for this purpose right now. This is just a regular fusion reactor. We're only getting 18,000 seconds of ISP, which is barely enough to get around the solar system with a reactor like this. So don't pay attention to the delta V. Let me close that. But under normal circumstances, you gotta be taking a lot of time, and for most of the trip, this hydrogen is just gonna hang out until you get to the end of the trip. If they are going to settle in the other star system and stop there, and they're just not going to leave, and they're not gonna come back, then this could be the fuel to capture at that star system. And once you're there, you don't need this shield anymore because you're not traveling very fast. So you could just use a tank. Now it needs to be sort of segmented up. They have to be able to patch it and stuff like that. But that's now another layer of protection aside from our liquid droplet radiators. And then the next level of protection is the actual radiation shielding on the rotating habitat itself. Because in addition to this liquid hydrogen tank, we're probably going to have some liquid propellant tank, maybe water or other tanks surrounding the habitat, because those need to protect it against radiation. Now, again, it's dual purpose. We need that propellant or water or whatever other supplies anyway, but they're got to be directly over the habitat, ringing it so that they can block radiation, cosmic rays and stuff like that. So, again, dual purpose. We need the stuff anyway, but again, protection, another layer of protection against micrometeorites or stuff like that. So, as far as I'm concerned, we're not looking at packing a separate shield. We're looking at using elements of our existing structure as shielding, as long as it's prepared properly. It'll add a little bit of extra dry mass, but it's nowhere near the kind of dry mass it would be if you had a different sort of arrangement. And I think this method of using the liquid droplet radiators in particular is perhaps innovative. I haven't seen that anywhere else. I just thought of it. So maybe it'll work. I thought of it, and then I went, hey, I went to ChatGPT. Okay, I said, hey, ChatGPT, could we do this? I wanted a sanity check. I said, well, sort of. It wasn't the first thing I thought of. The first thing I thought of was just putting the radiators up front and having the radiation sort of repel the particles, because, you know, we've got infrared radiation that will create a pressure in front of the vessel. And that's going at the speed of light anyway, just like all photons would. But ChatGPT shot that down and said, well, you're going to impart an acceleration on those little particles of 10 to the negative 17 meters per second squared. So, no. No, you're not going to be able to use your actual infrared radiation as a way to block particles from attacking you. And then they came up with the liquid droplet thing, and then it went, well, yeah, okay, maybe that could work. But you're going to lose some radiator efficiency because you need to pack the liquid droplets closer together to make it effective. But even if they're not packed close together, this method, one layer of this would still block most of the particles, more than 50%. So even if they're at optimal efficiency spread out, they would still block about 50% of the particles. So that's what we're looking at there. So these are just things that we could come up with right now. I'm sure as we actually tackle this subject more properly, we could come up with other things. But frankly, I don't think that the keeping the crew safe from incoming particles thing is going to be a deal breaker. I mean, it's going to be a problem, but it's not going to be a deal breaker. So once again, not impossible, just really difficult. But a lot of this difficulty in particular is going to be solved with just building it in space. After all, the fact that there's going to be extra mass is, again, going to be built in. We're largely going to be carrying this extra mass. As long as that's true, as long as the mass that we're going to be using is largely going to be mass that we're carrying anyway, we're in much better shape. And so the key to the design of spaceships is to make sure that's how it works. Not that we've got dedicated systems, each doing a separate thing. This is on a particular spaceship. I do approve of spaceships being designed for their purpose, like a special Mars lander, a special lunar lander, and especially designed vessels to go from one place to another. It's just that on a particular ship, I want the systems to be able to handle multiple tasks, and that will reduce the mass of that. And actually having dedicated ships doing each task also reduces the mass of each particular vessel so that they aren't carrying extra dry mass. For instance, Starship having to carry its tiles between Earth and Mars. Of course, I violate this myself with my own Asuka spaceplane design. Let's not talk about that. Anyway, so with that, that's my discussion on the debris and the micrometeorites that might be coming in. I just wanted to offer this more novel arrangement instead of having endless Whipple shields in front of your vessel. And so with that, thank you for watching. I hope you enjoyed this video. If you did, please do press like. If you have any comments or suggestions, please leave them in the comment section below. And I'll see you next time.